All right, so we had already indicated last time that we were going to be studying magnetic flux in this chapter, in chapter 30. And so magnetic flux can be thought of kind of analogous to electrical flux. Electrical flux was like the amount of electric field that passes through a surface. So magnetic flux is going to be the same thing. So we remember electric flux was the integral of of E dot dA over the surface. So by analogy, magnetic flux is going to be equal to B dot dA. Okay. If you had magnetic field and there's your magnetic field, you had a coil wire. So I'm going to have a coil right there. Okay. And the coil is going to have a certain number of turns in it, N turns. Okay. Now, if I were to look at it this way, so I put my eye right there and look at it, I have a coil right here, wire going around N times, and the magnetic field is going away from me like that. So the flux is going to be, the magnetic flux here is going to be equal to the area times B. Okay, if it's a circular coil like that, then the area is pi r squared. So this would be this would be, not 2, but this would be pi r squared times B. Now, you got the coil here, but if the coil starts to spin, so let's say we spin about an axis that's perpendicular to the screen here, so it turns by an angle. Now, what happens is that the flux through there is no longer as much flux as originally was because now the perspective has changed. And so because it's a dot product, if we imagine a perpendicular to the coil, the angle through which it turned is we call theta. So the B dot dA becomes B dA cosine the theta. Okay. So let's consider, therefore, that we've got coil. Let's say that it has 125 turns. Let's say that the radius of the coil, let's say it's a circular, so the radius is going to be equal to 8.25 centimeters. And let's say the coil is spinning with a frequency of 120 hertz. Now, because it's spinning in this magnetic field, the flux of the coil keeps changing. And since the flux keeps changing, what that means is that you induce an EMF in the coil. Basically, this is how you make a generator, is you spin a coil in a magnetic field, and that produces an EMF. And so I want to know, what is the voltage induced here? Well, the other thing you need to know is you need to know the magnetic field. So let's say the magnetic field is 0.141 Tesla. Okay, so what do? Well, we know from Faraday's law that the EMF is minus the rate of change of the magnetic flux. Okay, so it's going to be the derivative of the magnetic flux. Well, the magnetic flux here is going to be equal to N times B times A times cosine of the angle. Okay, and so derivative here, N, B, A is pi r squared, and cosine of the angle. Well, the angle keeps changing. So we remember from physics 1 that we can write that as omega t, angular velocity. the angular velocity is related to the frequency as 2 pi f. Okay, so I plug that in here, 2 pi f t. Okay, so now all we have to do is that derivative to find the EMF. So the EMF is minus, okay, so this is going to be equal to n b pi r squared 2 pi f sine, make that plus, 2 pi ft. Okay. So now all we have to do at this point is we plug in the numbers that we have. And when we do that, we find that the EMF is going to be 284 volts sine 753 hertz t. Now remember, that is 2 pi f because that is omega. So that's the angular frequency. That's not the actual frequency of the voltage, but that's the angular frequency right there. And so this gives the EMF. So it's sinusoidally varying. It's an AC voltage. So it keeps changing sinusoidally right up here. And this is the amplitude of the change. Okay. Well, this actually is an interesting thing because if you think about how a power tool works, so you have a power tool, so you plug it in, okay, so now your power tool here, okay, let's just say it's a plug-in electric drill instead of a cordless one, so when you plug in, and the armature, which is basically the coil in there that the current is going through, has resistance. All wires have resistance, so let's say it has resistance of 11 ohms. And so over here, we have 120 volts. Now, I know it's AC, not DC, but let's just pretend, okay, because you can think of this as a circuit, okay, and if you think of it as a circuit, naively, you'd say, well, how much current does the drill pull? And so the drill is, you would think, well, the current is going to be V over R, so of 120 volts over 11 ohms, okay, and so that would be 10.9 amps. Okay, except it doesn't really work that smoothly or exactly that way because inside here is a coil. That's how the motor works. We talked about how motors work before. You have a little coil in there and you have current going through it in a magnetic field, and so that produces a torque that drives the motor. But because you have a motor, which is a coil spinning in a magnetic field, then what that does is it makes an EMF. The EMF is going to be resisting the change, so that means we have what we call a back EMF. So the back EMF, let's say it's equal to, let's say that it's equal to 75 volts. Okay, and so what's going to happen is this is going to act like it is going to act like 120 volts. Okay, and then it's going to act like there's a backwards EMF in here is 75 volts, and then an 11 ohm load. And so if you work that out, then the current is going to be 120 volts minus 75 volts divided by 11 ohms. And so that's going to equal 4.1 amps. Okay. And so what you notice is that under load, then once it spins up, when you first, in fact, this is something that actually happens with a power tool, is when you first plug it in, before the motor starts spinning, it takes a lot more current than it does once it spins up to full operating speed. Because once it's spun up to operating speed, you have the back EMF, which is actually slowing it down. So now the question would be, suppose your power tool is spinning at half speed. So you're putting it under load, it's not spinning at full speed. How much current does it draw? So the question is, what's the back EMF? Well, the back EMF is 75 volts at full speed. The back EMF is 0 volts when it's not moving. So at half speed, what's the back EMF? Well, it's not really all that complicated. It's going to be half of the full EMF. So in other words, 37.5 volts. So now the question is, how much current would the power tool draw if it's spinning at half speed? So the current would be 120 volts minus the back EMF, which is now 37.5 volts, divided by the armature resistance. And so that's going to be the current drawn by this thing. So that'll be about 7.5 amps. Okay, so that's going at half speed. Okay, and so this is just another application of these coils spinning in a magnetic field.